All right, strength and conditioners. Welcome back to another lecture. Today we are going to talk about lecture 3B. We're talking more about physiological adaptations to resistance training. We talked about some basics in 3A. And now we're going to get into some more physiological changes that happen with strength training. We're also going to throw in a little bit of conditioning today as well. We're going to start moving into more of kind of athlete-centered, athlete-focused strength and conditioning concepts and things we need to consider when we are training our athletes. Essentially, I am giving you the tools, I'm giving you the puzzle pieces, and you guys are going to use these things to kind of put together to condition an athlete or to strengthen an athlete. And as you know by now, athletes are snowflakes and fingerprints, right? They're all completely unique from one another. Even if you have athletes on the same team, right? A goalie on a hockey team is way different than an enforcer on a hockey team, and you got to train them completely differently. A midfielder on a soccer team is different than a frontline left-wing striker on a soccer team. So they all require very unique consideration and very unique training regimens to get them where they need to be. In this lecture, we're also going to start kind of touching the surface on some of the cellular adaptations that happen. We'll be talking about some growth factor, testosterone, things like that, that are associated with changes in the body due to stimulus of strength and conditioning. So we're going to get into some of the cellular stuff, and the cellular stuff is going to come from the NSCA textbook, and I will inform you of when I'm kind of shifting over to the NSCA content. So what we have covered so far has had about 75% from the Flex textbook and then about 25% from the NSCA. I'm just kind of flip-flopping those two and going back and forth and providing you all the information that you will need for your CSCS exam. So with no further ado, let's pick up where we left off and start talking about some of those adaptations that we get when we are strength training, and we're focusing primarily on strength training right now. I will bring in conditioning over the remainder of this lecture, and as we get into next week's lecture, we'll talk more about the conditioning component. But it's always a good idea to start most of your regimens off with strength, because all these other skill fitness components are going to build off of strength. Okay, if you have a strong muscle and that muscle is coordinating with all the fibers within that muscle, right? You have intramuscular coordination, which is going to come from neurological adaptations. Then the muscle, those groups of muscles are going to put out more force, and they're going to do it at a much faster rate. And it's going to increase coordination, it's going to increase speed, it's going to increase power, it's going to increase reflexes. So all of these things are associated with adaptations that we get from strength training. And once we get those adaptations, then we have to kind of sharpen some of those skills with conditioning. So if we think about a sword, the strength will give us either the width or the length of the sword, and the conditioning will sharpen the edges, right? So if we do very little strength training, we'll have like a little baby dagger, right? If we do a robust strength training regiment, then that sword will be like one of those broadswords, those very long ones, and the edge will be razor sharp. So kind of think of it that way. So when we left off on the last lecture, we were talking about some of the changes that are going to happen to the body via strength training. We talked about some of the neurons and some of the basics. One of the other things that's going to happen is we're going to have changes in myoglobin. So what is myoglobin? Well, essentially, it is a protein that is found primarily in contractile skeletal muscle, okay? And it has a very specific job, and you guys probably know this, so we won't stay on this too long. But myoglobin has a heme prosthetic group, and that heme prosthetic group is very similar to what we see in red blood cells with the heme groups. It has the capacity to bind oxygen and release oxygen. So myoglobin is going to be a way for oxygen to be stored in contractile skeletal muscle. So it's going to serve a purpose to basically control oxygen coming in from red blood cells and saturate the muscle with oxygen, and it's going to play a different role in different fiber types. So if we consider fiber types, we know that type 1 is an oxidative fiber. We know that it's robust with mitochondria. We know that it likes rhythmic continuous contractions that we would see in running or walking and cycling. And we know that type 2A fibers is a strength fiber, and we know that that favors glycolytic processes, so it likes to use glucose, whether it's anaerobic or aerobically. So because it has that anaerobic and aerobic component, we know that type 2 fibers are going to have some mitochondria, not as much as type 1, but it will be mitochondria dense. And then we have the type 2X fibers, which we know are primarily phosphogenic, have very little mitochondria, so serves a very different purpose. Now, those fiber characteristics are all going to require different myoglobin, and the more mitochondria we have, the more myoglobin that is necessary. So think about what those ratios might look like. So here's just kind of a picture to show you. We have a muscle here, and then we have a muscle fiber, and here we have the myofibrils, right? We have those smallest contractile pieces that we talked about that contain the sarcomere. And then we have sorry about that. This thing is so sensitive. Here we have the myoglobin protein, and we can see that oxygen is bound to it, and it's bound to these heme groups, right? And we know that this protein is in the sarcoplasm of the muscle fiber, right? So it's floating around in that aqueous solution, and it's going to be able to provide oxygen to muscle fibers that are rich with mitochondria. So if we were to look at this scheme here, we can see that red blood cells are traveling through the circulation, right? This could be a micro vessel, probably a micro vessel, which is capillaries, right? Because we know that the exchange of oxygen happens within the micro vessel, which is the capillary network. We can see that the red blood cells here have hemoglobin. We know that hemoglobin binds this oxygen. And when we have a decrease in pressure, well, that tells the oxygen to be released from the hemoglobin to diffuse into the skeletal muscle, where it will bind to myoglobin, and then myoglobin will kind of hold on to that oxygen and then deliver that where it needs to be, which is the mitochondria, okay? So the red blood cells and the skeletal muscle tissue require a relay system where the oxygen is delivered from hemoglobin to myoglobin. Now, to go back to that fiber type specificity, when we take muscle biopsies of skeletal muscle and we look at it under a microscope, we can apply these different stains or dyes. So imagine if you have a deck, right? You just sanded a deck outside and you want to stain it a certain color. That deck is going to suck up that stain and change that color very quickly. We can do the same thing in the lab. So if we do a muscle biopsy and we do a cross-sectional analysis of that muscle that we took a biopsy of, we can put various stains on it, and those stains will react with the myoglobin. And when we put a light under that tissue sample, that light will show us 3 very different colored muscle fibers, and it will look something like this, right? So if we had a lot of myoglobin, that is going to be a red fiber. And if there's a lot of myoglobin, we know that that is going to be an oxidative fiber, because where there's mitochondria, there is myoglobin, and lots of it. So we can tell the composition of somebody's muscle by the different colors that we see. So if we have a deep red, that tells us that's a type 1 fiber. If we have a pink color, then that tells us it's a type 2A fiber. So we know that's a strength fiber, because strength fibers could use glucose anaerobically or aerobically, right? So it would make sense that type 2A are going to have some mitochondria, but not as much as type 1 fibers. And then when we move to a type X fiber, well, I told you a type 2X fiber, I told you they don't have very much mitochondria at all. They are phosphogenic in nature. They have a very quick fatigue rate. So those fibers aren't used very much for oxidative functions. So we can look at somebody's composition and see these 3 different colors, and we can tell that that individual is potentially a runner, or that individual, if they have more of these fibers than anything else, that individual is a strength athlete, or maybe that individual is an Olympic high jumper and they have more of these fibers than anything else. So it kind of makes you wonder if nature gives us fiber characteristics that just make us natural athletes, or can we change the composition of these fibers through stimulus? Which is, if I just want to strength train and I don't do anything else and I strength train 6 days a week, will some of these fibers begin to convert into these fibers? So if I looked under a microscope 6 months after strength training, will I see way more of this color than this color? Or will there be a conversion of some of the type 1 fibers to type 2A fibers? Yeah, there are conversions of fibers. There are hybrid fibers that we get when we do certain types of exercises. So that's the myoglobin story. So what happens when we begin to strength train is we have a decreased myoglobin content, and we have it specifically in those type 2A fibers. Why does that happen? Well, because we're training the muscle in a certain way where it's becoming less oxidative. Now, if you're going to do cross-training, that might not be true. Now, if we cross-train, we might not get the same strength gains as if we were just strength training. But if that's not your focus, then total strength doesn't matter. If we do need some oxidative capacity, well, then we might not get as strong because we have to run. But if that is a functional choice, and that's going to help us in a sport, then that makes sense. If you look at the world's strongest man contest, right? They have those guys like whose names are like Hercules or Maximus, right? And they're all from Iceland or Sweden, and they're like sides of beef, like 450 pounds, and they have just a gut that's hanging over their, like, you know, they can't even see their own feet because their gut is so big, but they're, you know, bench pressing semi-trucks. Those guys, all they do is strength train. They're not running, they're not sprinting, they're not jump roping, they're not hitting the hills and cycling, they're not swimming. They have a very specific phenotype, which is purely strength. So those individuals are going to have way less oxidative capacity because they are training in a very specific way. All right. Versus, let's say, an MMA fighter who, yes, they do strength training, but they also do bag work. They also do mitt work. They're also running 8 miles a day. They're also doing wrestling. They're also doing jujitsu. Strength is important to them, but it's not everything. Strength is just one piece of their puzzle, where if you have the world's strongest man contest and you have Maximus that is trying to bench press 2 semi-trucks, they're not going to do mitt work. They're not going to do bag work. They're not going to do jujitsu, right? So for them, that stimulus of only strength training works. It's meaningful and it's purposeful. Where the MMA fighter, if all they did was do strength training, they'd get in the cage and get murdered, right? So these training regimens have their place in sports, but you got to figure out where that place is. Okay, so the point I'm trying to make is, if we only do strength training, we're going to have a decrease in myoglobin. That is one of the adaptations going to happen. It's not detrimental. It's just the stimulus that's coming in is strength. It's glycolytic in nature. It's really turning on those type 2A fibers. So there are going to be adaptations that happen. The other thing that's going to happen is we're going to have increased capillary density in type 2A fibers. So that means that the network of delivery vessels that are going to bring in nutrients, bring in glucose, bring in immune cells to help repair, that network is going to become more vast, which is going to be beneficial. But also, if we have a more vast network, we're going to have the removal of metabolites be much quicker and much greater, right? So CO2 will be removed faster. Lactic acid or hydrogen ions will be removed faster and buffered in the blood. So if you look here, you can see that this would be a muscle biopsy again. If we were to do a biopsy and I were to lay the piece of muscle on a table and we all looked at it from a bird's eye view, this is how it would look. You can see the myofibrils here. You can see the white space in between. That would be the interstitial space. And here you can see capillaries, right? So we can see that there are capillary networks all around each of the myofibrils. Now, this would be pre-training. Post-training, if we were doing strength training, you would see that same muscle biopsy from that same person would look like this. So you would see that the mitochondria the capillary density is much greater in a trained muscle. So we do get more capillaries, and this is proof that that happens in skeletal muscle. The other thing that happens is we get way more nuclei, and that makes sense as well. So if you look down here, you can see that these tissues, if you look at this fiber right here, this is a really interesting fiber. It has 1, 2, 3, 4, 5, 6 nuclei just on this surface here. So we get more nuclei on those muscle fibers as a result of strength training, and then causing microtrauma, and then initiating the repair process, which you guys remember is secretion of satellite cells and the proliferation and differentiation of those satellite cells, and the binding of those satellite cells to the fiber that is injured, right? So that's where we get hypertrophy and hyperplasia. We talked about that in previous lectures. And then the muscle cell becomes more multinucleated, which means then you have more control over that specific fiber, because I like to call nuclei computers, right? You have more computers focusing on a single fiber, which is going to have much more benefits over a lifespan and help fighting off disease. So these are some changes that happen. And ultimately what happens is those type 2 fibers, they just become less oxidative, right? And if that's your goal, if that's what you want to do with strength training, then you focus on the strength training and you leave out all those other sort of skill fitnesses or all those other types of training modalities so that you can get these adaptations if strength is your primary goal. So some other things that are going to happen is if we look at this one here, this shows you an untrained fiber. So I'm just kind of building on that multinucleated theme here. We can see that when we're untrained, we have 1, 2, 3, 4, 5, 6. We'll say 6 little computers on this fiber here. And then as we start to get bigger, right, so we get hypertrophy, we still have 1, 2, 3, 4, 5, 6. Then we have microtrauma and tears, and those satellite cells come and they begin to fuse to that same fiber, right? So that we were working out, and now we have more of those satellite cells there. So now we have 6, 7, 8, 9. And then after repair, look at this. We have so many more nuclei. So why is this beneficial? Well, for the first thing, like I said, you have more computers focusing on a single fiber, which means that adaptations can happen quicker, which means repair can happen quicker, which means that those computers that control the fiber, they're much more in tune with the fiber. The other thing that there's speculation about is children. So children that are brought up exercising, so we call them lifelong exercisers, right? And they get into their adult life and they're exercising. Well, they seem to have an advantage that sedentary people don't. So think back when you were a kid, if your parents had you in basketball and then they would pick you up from basketball and run you to, let's say, soccer, and then on Thursday you had dance, and then on the weekends you were outside playing with your friends. Well, all of those activities were causing trauma to the fiber and causing repair to the fiber. And over the course of those years, all those years of playing outside, you began to creating this multinucleated fiber with every muscle in your body. Every myofibril in your body was undergoing these adaptations. So by the time you're 15, 16 years old, most of your myofibrils look like this. They're multinucleated, okay? And they're speculating that individuals that are lifelong exercisers can recover from injury faster and can basically get back what they lost after an injury much faster. So let's imagine you're a tennis player and you played tennis most of your life, and then you had a horrible injury. You had to get elbow surgery, you had to get shoulder surgery, and you couldn't play tennis for 8 months. You had to undergo rehabilitation, you had to undergo physical therapy. Well, all those adaptations that happened as a kid, all that multinucleation that occurred, is going to help you repair that injury faster, and is also going to help you bounce back faster. And that's where muscle memory comes from. It's not necessarily the memory of the movement, but it's the fibrils, the myofibrils, that are remembering the metabolic process, remembering the contractile process, right? If you're a tennis player, let's say you had an injury on your shoulder, is that shoulder when you're swinging a racket, is it a fast contraction or is it a slow contraction? Those nuclei are going to memorize those characteristics and it's going to memorize the force output and the contraction type and how frequently the myosin and actin were making cross bridges and how much power you were able to put out. And you'll be able to bounce back into that sport much faster because of that. So these are speculations that they're doing research on now with, population of nuclei in muscle. So the takeaway message for this is, if you have children, or if you're planning on having children, shut off the TV, shut off the tablets, and tell them to get their asses outside and to exercise as much as they can, because they're going to grow up in their adolescence having fibers that look like this versus fibers that look like this. So these would be individuals that are very sedentary, and ironically, those that sit on the computer all day or in front of a computer, the irony is they have less computers kind of monitoring and programming their muscles, right? So something to think about. And then one of the last adaptations that's going to happen is, if I told you those muscles, type 2 fibers, are going to become less oxidative with strength training, primarily strength training, we're going to have less mitochondria density. And that makes sense, because we're going to have less myoglobin. So those mitochondria fission-fusion processes and those networks are going to become less robust. And it's not going to cause any damage to the muscle. It's not going to cause any issues to the system like we would see in a disease state, but we're just becoming less oxidative. And that's because of the stimulus, right? This is because of the training. So things to think about. Now, something else we talked about was neurogenesis. We talked about how the alpha motor neuron here stimulates muscle fibers, and we see that here in the axon terminals, right? Well, we know that when we exercise, we're going to have more innervation. We're going to have more branching of these neuron terminals here. And that means we're going to have more recruitment of muscle fibers, and we're going to have more recruitment of more muscles, right? So we're going to have greater coordination of muscle fibers. And if we have greater coordination of muscle fibers all firing at once, that's going to increase force output. That's going to increase strength. That's going to increase power. So if we have more neurons communicating with the muscles, those muscles will contract at a much faster and more forceful rate. You guys know that. So let's look at a picture of it here. Here we can see some immunohistochemistry staining here. We can see a primary neuron here. We can see that we have the alpha motor neuron here. You can see this kind of green area right here. This is the sarcolemma of the muscle. You can kind of see it here as well. And the red would be the neuron axon terminal, where the vesicles are released, where the synaptic cleft is. And we can see that we have a primary alpha motor neuron here. And it is, we can say 1, 2, let's just kind of try to quantify this. 1, 2, 3, 4, 5, 6. It looks like it has 6 finger-like projections that are communicating with the muscle. Now, you can see some branching occurring here off of this alpha motor neuron, and we can see that this branching, it now brings about more axon terminals. So now we have the 6 over here, and it looks like we have possibly another 6 and another 6, so we have 12, okay? So with exercise, with strength training, with these neural adaptations, we increase the population of neurons that can send that signal to the sarcolemma. Now, if we just had this alpha motor neuron here, and it was just kind of communicating with this fiber that's right here, and we were trying to bench press, say, 100 pounds, that might be strenuous. But if we keep delivering that strength training stimuli, then we have this branching of the neurons, and now we have these neurons communicating with these fibers here, and now we have the coordination of this fiber and looks like this fiber. So if we add an additional fiber to come to the rescue of this fiber, then bench pressing that 100 pounds becomes very easy, because we are recruiting help from other fibers. So that's how that works. Now, these two fibers working together and coordinating their movement together would also increase force and also increase the time, make force production at a much faster rate. So we would be able to produce force much more quickly. So that is how that adaptation helps us build strength. when we have the branching of neurons and we have neurogenesis occurring, it is recruiting help. It is recruiting more fibers to come to contract against the weight that we are trying to lift. Thereby, if we recruit more fibers, we can push up more weight. You guys know that. So another kind of cool adaptation that occurs with strength training has to do with the disinhibition of these inhibitory mechanisms that we have located around or near the motor neuron. So these are mechanoreceptors, things that you are well aware of, such as the Golgi Tendon organs and the Renshaw cells. So what begins to happen is, as these governors, these organs or cells in our body that regulate how much force we are allowed to generate, and they do this, they regulate this to protect us, because if we were left to our own devices and we tried to do a 2,000-pound squat just to impress ourselves and others, we would essentially tear the muscle from the tendon, tear the ligaments in the joints. We'd absolutely destroy some of the architectural components in our body, right? So the body is smarter than we are, and it has ways to basically protect us from lifting too much weight. And one of the things that happens with strength training is those protectors, they begin to kind of lessen up their governing responsibilities a little more. So they become a little less strict on how much weight you are allowed to lift. So let's talk about how the disinhibition will affect these two mechanisms here. So basically, they'll become a little less strict in regulating how much weight you can put up. So we know that the Golgi tendon organs, these are sensory receptors, right? And we know that they are located in the myotendinous junction, which is here, where the tendon connects with the bone and where the tendon connects with the tissue. So these bundles of essentially this neuron bundle in this myotendinous junction is really sensitive to pressure. And when a muscle receives a lot of pressure or a lot of force, then that pulls on that junction there, that pulls on that myotendinous junction, and the Golgi organ essentially stresses. So if there's too much force, if that is being generated in the muscle, the Golgi tendon becomes activated, and when it's stretched, it will essentially begin to, it'll depolarize, and it will send these messages to the brain, right? So afferent signals would be sent to the central nervous system and out to the brain, and the brain will process that information and say, okay, it's too much weight, it's too heavy, and we are going to inhibit that muscle action. So you can see here that the signal, there's a stretching on the Golgi tendon. The stretching causes action potential. The greater the stretch, the more action potential that fires. That is sent out to the central nervous system and to the brain. The brain processes that stretch, and it basically governs that action. It puts an inhibition on that action. So it will efferently send a message back and stop that muscle from contracting to protect ourselves from essentially ripping the tissue from the tendon. So it will decrease the muscle contraction and the muscle force, and it will inhibit the action, okay? So now, basically, as we get stronger, the Golgi tendon organ, it becomes less strict on governing because it realizes that the muscle is going through adaptations. The muscle's getting bigger and stronger. Therefore, it can increase more lifting, because how strange would that be? More weightlifting, right? So how strange would that be if the muscle's getting big and you're working out more, and that Golgi tendon organ wasn't inhibited? It would essentially create a ceiling on how strong you can get. So there's a direct relationship between the muscle size, the Golgi tendon, the efferent neuron, the central nervous system, the brain, and then the efferent and afferent neurons that send the message back as well. So all these things this is a reflex arc, right? So it's an arc where we have this kind of cyclic message being sent and receive, and basically telling the muscle to either to stop contraction or to. So what happens is when the Golgi tendon recognizes this signal, the inhibition stops. The inhibition is at this muscle here, right? So if we're doing a curl and it's too much weight, the brain will inhibit this muscle, but it will strengthen the contraction of this muscle back here, right? Therefore, it will create more stability for holding that weight. So I hope that kind of makes sense, okay? And let's look at this a little bit more. So here is an actual picture of the Golgi tendon. So we can see here it's in this tendinous tissue where the tissue meets with the muscle. And here you can see that afferent neuron is kind of leaving to communicate with the central nervous system and the brain. So when we are exercising, if a degree of force is too high, then the Golgi tendon triggers the contractile muscle to relax and the antagonist muscle to contract. So if we look back here, we have the contracting muscle and the antagonist muscle. So it will relax this muscle here and increase the contraction here so that it protects this entire structure here. It protects the joint, the tendons, the ligaments, everything associated with it, right? So it's protecting us from ourselves. So what does that look like? Let's say this strong, strapping young lad here is curling 75 pounds. Well, let's say 75 pounds is this individual's 60% of his 1 rep max. So in this condition here, since it's 60% of the 1 rep max, the Golgi tendon organ is off. It's really not threatened. It's not really seeing any threats with this weight, simply because this is a controlled movement because it's a load that this person is comfortable with. So if this person moves up to 100 pounds, and let's say that's 90% of their 1 rep max, now the Golgi tendon organ is active and it's on alert. So it's already kind of communicating with the central nervous system and the brain, and it's starting to monitor this movement. And what has done that? Well, it's the increase in load from 75 to 100 pounds. So we have a 25-pound addition here, and that is causing the Golgi tendon to be on high alert. Now, let's say this guy tries to pick up 200 pounds and tries to curl that. Well, that is going to have a major impact on the myotendinous area here. And the Golgi tendon organ is going to be fully activated, and it's going to inhibit this muscle contraction while increasing the contraction of the antagonist muscle, so that this individual can't lift this weight and put himself in the hospital because he tore the muscle from the tendon. So that is how that works. So as we start to get stronger, we have the disinhibition of the inhibitory Golgi tendon organ. Let's try to say that 20 times, okay? So if the Golgi tendon organ is a very strict parent that is monitoring everything you do, well, as you get bigger and stronger, that parent becomes a bit less strict, and it lets you get away with a little more, okay? So it lays off a bit. So that is one of the cool things that happens when we start to increase in strength. And if you think about it, if the Golgi tendon did not loosen up the reins on inhibition, you would never get hypertrophy, right? So there's a direct relationship between muscles that are allowed to get bigger and the reduction in monitorization or the governing of the Golgi tendon organ. So pretty cool relationship. So another pretty cool mechanism are these Renshaw cells. Renshaw cells. Say that 20 times as well. Renshaw cells. So these are connecting neurons that are associated with the motor neuron, right? So you can see here that we have a motor neuron here. We have a motor neuron here. These are going to send out different muscle contraction signals that we'll call twitches, right? And if we have a signal here and a signal here and a signal here and then a signal here, those signals will begin summation, right? And then if summation occurs and it's uninterrupted, then we'll have tension, right? We'll have muscle contraction that will happen. So another one of these inhibitory mechanisms that protect us from lifting too much weight is at the motor neuron, and it's these interneurons that will dampen the rate of motor neuron discharge, right? So it will dampen the recruitment of muscle fibers by these neurons. So if you can see here, the Renshaw cell, you can see the minus sign, it will inhibit summation. You guys should all know what summation is. If you don't, I'll kind of look at it on the next slide for you. And this is going to limit the tension formation. So these are responsible for recurrent inhibition. And again, this working with the Golgi organ, work together to limit the amount of weight you can lift, to limit the chances of you becoming injured. So it helps protect muscular damage. So these cells also reduce their inhibition as we begin to get stronger, because think about it for a moment. If these did not loosen up the reins a little bit, and the Golgi organ didn't loosen up the reins a little bit, they would constantly be communicating with the brain, and the brain would be inhibiting the muscle action and telling the Renshaw cells to inhibit twitch and summation. Thereby, you wouldn't be able to lift any more any more weight. So there's this really cool relationship with all these different mechanisms that govern us and protect us, and as we get stronger, they begin to loosen up a little bit. So you can see that these are located within, spatially located between other motor neurons. All right, so pretty cool inhibitory mechanism that loosens up a little bit when we begin to get stronger. So if we look here at force production and we look here at time, this is time, right? We can see that as these neurons begin to fire, we know that one of them sends a twitch. There's another twitch that is summated on top of this first twitch, and we can see that with the first twitch, we have low force production, but then when another neuron fires and it recruits more muscle fibers, look at this, we have greater force production. And then if we get, let's say, this guy here starts to fire, well, then we have another summated twitch, which builds upon this, and you can see that over the course of summation here, we have more force being produced, right? And what happens is these Renshaw cells will inhibit tension if it is too much for us to lift, right? It'll basically inhibit these twitches, and it will stop summation, and it will stop the formation of tension. So that is how those work. So these are governing what the alpha motor neurons are telling skeletal muscle to do. And if you're not really familiar with cellular mechanisms and cellular pathways, whenever you see this little T like this, that means inhibition. So it stops this. So that is how that works. So this guy here will stop the summation process, which will stop multiple fibers from creating tension at a single time, therefore stopping how much weight you can lift. Okay, so on those last few sets of slides, we really talked about how strength training will cause the inhibition or the de-inhibition of inhibitory mechanisms that will allow the muscle to get bigger, allow us to get stronger, and kind of lessen the governing oversight a little bit. So now let's talk about some other positive adaptations to strength training, and one of those is intramuscular coordination. So what does that mean? So that means that all those individual fibers in your muscle, they're going to be recruited and starting to build tension together in uniform, right? And what's going to happen when that occurs? Well, when you have intramuscular coordination, that will allow you to build more tension. That will allow the muscle to build more tension to overcome heavier weight loads. So one of the ways that happens is through this process called synchronization, and you guys can read this, okay? And basically the firing rates of the neurons and the muscle building tension begins to collaborate and work in unison and work together to build more capacity to put out force. So we have the synchronization of the motor unit, and we have the synchronization of recruitment of individual muscle fibers. Now, what's interesting about this is that the muscle doesn't necessarily have to get bigger to do this. So this is the relationship between the motor unit, the neurons firing, and the muscle fibers building tension and doing so together. And then the last thing that happens is that we have an increase in rate coding. So that means that we increase the firing rate of those alpha motor neurons that will start to communicate with the fibers. So what does that rate coding look like? Let me just kind of draw something here. So let's say that when we have these individual neurons firing, let's look back at this page here. Here we can see that we have a twitch, right? So a neuron is firing, it's depolarizing, and then it is repolarizing. But when that happens, we have another neuron firing, and that is building upon the twitch, the signal that is being sent to the muscle. And then we have the repolarization, and then we have another neuron firing. And what happens is we start to I'm going to just kind of draw this dotted line here. We start to build more tension in the muscle. So what started here, when we have summation of signals, we have the capacity to produce more force, all right? And when we increase the firing rate, so if we look back at that last slide, the firing rate kind of looked like this, right? So if we have a deconditioned muscle or individual or motor unit, the firing rate might look like this, all right? Where we have this kind of space between the signals from the neurons. Now, when we start to work out and we increase how many times a week we're exercising, we're doing it frequently, then the rate coding might start to fire like this. Okay, now what's the difference between these two? Well, they're much closer together. So that means that the signal is firing at a much faster rate. And if it's firing at a much faster rate, well, that is going to recruit the fibers much quicker, which would have an impact on individual fibers beginning to synchronize and contract together. So let's look at what that looks like on this next slide here. So here we have a picture of an individual that hasn't been training, right? So we have an initial value. Here we can see strength capacity. Here we can see, if we have a cross-sectional evaluation of skeletal muscle, we can see that there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We have 10 fibers here. Now, before exercise, we only have recruitment and synchronization of 6 of the 10 fibers. Okay, this is a very generic representation. This is kind of true over here as well. You can see that, before we begin to exercise, we have more. Or here we have recruited on the outside and non-recruited on the inside. So there's no synchronization here. Now, as we begin to move deeper into our exercise regimens, we're a couple months in or a couple weeks in, what begins to happen is we begin to get more recruitment, right? So now we have 8 versus 6, and these are synchronized. And what happens is we move from here to here. So because there is an increase in rate coding, there's an increase in muscle fiber recruitment, and there's an increase in synchronization of the fibers, we have a growth in strength. Now, this would be the first cycle. So let's say we're second cycle. So we're now into our 3rd or 4th month. And what begins to happen is the muscle's not getting any bigger, but these fibers are starting to synchronize even more so. So now we have the recruitment of 9 fibers synchronized. Rate coding is increased, and look what happens here. We have an increase in strength again. So this is how all of that works. Now, let's look at the next slide. If we think about exercise, and we think about us as trainers, and we think about how we can kind of push our athletes into recruiting more fibers and synchronizing fibers and increasing rate coding, well, there's a way that we can cheat and make this happen. And this is what I do with my athletes all the time. Because I work with MMA athletes, and we are in every plane of motion imaginable. We are competing for anywhere between 3 to 5 minutes. It involves strength, it involves power, it involves agility. There's all these factors that we have to consider. It doesn't really do us much benefit to sit down and to do shoulder presses, or to sit down on some sort of artificial support and do rows for our back. So I'm going to walk you guys through a couple of examples to show you how we can nudge athletes to accelerate these adaptations in skeletal muscle and in rate coding. So give me 1 second. Let me get these videos ready, and then we will get into it. Okay, guys, so here we go. We're first going to look at some alterations in working the back and doing some rows. So I'm going to play a couple of just quick seconds here so you can see how we can alter these exercises to stimulate more of that synchronization, that rate coding, increasing the firing rate of those neurons, and also just burning more calories, right? Because the more muscles we activate, the more calories we burn. So it looks a little blurry. I'm having a lot of internet issues. So if this comes out horribly, I will put the links up to these videos so you can find them as well. So I'm going to play this, and you can see in this scenario, we have an individual that is seated. You can see here, she is activating her back, she is activating her shoulders, but she essentially has one primary mover, which is going to be all those muscles in the back. There's no stability work. The legs are not active. Her core is tight, but her core is tight in almost a completely isometric contraction. So although we'll build some muscle and build some strength here, we're really not stimulating or challenging that neural drive and those motor units to fire as much as possible. So let's pause here. Let's take a look at this next one. I apologize, this dude's a little weird looking. But we can see now that he is standing. The difference between this gentleman and this woman back here is she is essentially doing a bilateral movement. She has both hands on a single bar, where this individual is having unilateral. So each arm has to do its own work. The stronger arm can't cheat and overcompensate. So we'll get more strength adaptations that way. And also, because he's standing now, I'll press play. Because he's standing now, you can see that now he's activating the legs, he's activating the glute, the back is activated. He has every muscle in his body is contracting, which means that there is a lot of neuron firing, right? So we have almost let's just kind of go back a little bit. We almost have an isometric contraction here with the legs, right? Just maintaining that position. And then his primary movers are, look at those guns, my God. And then the primary movers are doing the work here. So in this position, we have quite a bit more twitching occurring, more summation occurring, more tension throughout the body occurring, more recruitment, and more synergistic muscle fiber contractions. So now let's look at another one. This is basically how I would train my athletes. So here we have another version of the row. But here we have 1 foot on, 1 foot elevated, contraction and tension created here, contraction and tension created here. This leg is stabilizing the entire body. We have posterior chain activation and contraction occurring, and then we're going to have primary movers that are going to be working as well here. So this would be an example of how we can kind of cheat and get more neural adaptations, get more strength, whole body strength versus just isolating a single body part, which in this case would be the back, and really creates a lot of neural drive. You can see here he's holding onto a ring, so a tremendous amount of core strength, balance, and synchronization of muscles. This woman here, she's on a stability ball doing the exact same thing. So the point to take away from this is we can stimulate recruitment, synchronization, and rate code firing by just changing the apparatus that we're working on, right? Here we have very little, and we can think of recruitment not just being a muscle group, but whole body recruitment, right? If you want to look like this gentleman here, this kind of weird alien looking dude, I guarantee you he is not doing a tremendous amount of whole body lifts. He is isolating, and because he's isolating, he's getting those muscles very, very large. Probably doing a lot of cycles of steroids as well. But when we go to this type of athlete, this is going to create functional strength in different planes of motion. It's going to create agility where, if you are doing running drills, both legs will be able to handle the load, and both legs will be able to switch directions very quickly because you're challenging balance within a single leg while being unstable, while lifting weight here. So this is how you would really kind of get those adaptations for recruitment and synchronization and rate coding. Now, what's the downside to this? Well, this type of exercise, you're not going to be able to lift as much weight as this type of exercise. So the downside is here you would have the lightest amount of weight. Here you would have the second, this would be heavier, right? And then here you would be able to do much more weight. So the more support you have, the more weight you can lift, where when you're doing something like this, you're doing something like this, there's very little weight, but the benefit to that is you're getting whole body recruitment, whole body synchronization, and you are getting every neuron in the body just firing at one time, right? There's no part of her that is uncontracted at the moment. So let's look at the same thing now with seated presses, and this is blurry too. I apologize, but let's kind of just get through it. So you can see here, this lady is seated. She has artificial back support. It looks like this is potentially a Smith machine. I can't tell because it's blurry. But here she is truly just kind of activating and recruiting and synchronizing those muscles in the shoulder, and then any kind of synergist muscles that are helping stabilize weight, right? So in the seated position, we're not getting whole body synchronization of muscle fibers contracting at a single time. Here you could probably do much more weight than the other options I'm going to show you. So let's stop here. What would be a modification of this type of exercise? Well, you should be saying standing right now, and here you can see this young lady is standing. When you stand, you have more activation of the legs, the glutes, the core. Again, you would not be able to do as much weight. The reason being is because now all that weight is compressing on the spine, where in the previous video you could see that the spine is being supported by this artificial support back here, so that would allow you to do more weight. And you can see that she is, doing a shoulder press in the similar fashion, but she is doing unilateral. So each one of these arms has to pull their own weight. They have to do the same amount of work, which is wonderful for reducing weaknesses in certain ranges of motion, where if we went back to this one here, when we do a bilateral, our stronger shoulder can overcompensate for our weaker shoulder. So obviously you would have more neural and motor unit adaptations in this type of exercise because each arm has to do the same amount of lifting, right? So you would have significant adaptations there, but again, you won't be able to push as much weight. Now let's look at something that would activate the entire body, would synergistically activate almost every muscle fiber in the body. It would increase recruitment of fibers, increase synchronization of fibers, and that rate coding, that firing rate of those motor units would just be very, very fast. So let's take a look at this. We have an individual here in a push-up position. You probably can't see it, but there's a band here, and this band, you guys know what the bands are doing. He's going to push the weight this way, and as that band gets tighter, it's going to challenge that strength curve a bit more. So let's take a look at this. Now, every single muscle is activated in this type of exercise. Here we have the lady just kind of having one foot off the ground, working stabilization. Here there's two bands, which is going to increase the strength, challenge that strength curve a little more. This gentleman's doing it with a trap bar. The eccentric and concentric contractions are both being challenged because that band is trying to pull that bar back, and he's slowly letting this weight kind of retract. So these are some subtle differences that we can do that we can use in the gym to challenge and to kind of accelerate those neural and motor unit adaptations. Now let's think about the Golgi organ, Golgi tendon organ, and let's think about those Renshaw cells. We would probably have more adaptations to those in this type of exercise because we're lifting more weight here, right? So that's something to think about. Here we would challenge those inhibitory devices a little less because we're standing, we're not doing as much weight as we would when we're seated. And here we might not be stimulating them very much at all. So you have to figure out what you're trying to do to your athlete or to you yourself and the adaptations that you're trying to gain. Okay, so one of the things I don't like about the word strength and conditioning is we always think of just building muscle and building strength. That's true to a point because we're building muscle and building strength in this fashion in an isolated manner. So that's not functional though, right? That's not going to make an athlete better at being an athlete. If you want to have ridiculous beach muscles like this guy, then go ahead, do that type of training, and you're going to get those adaptations if that's what you want. But if we're training athletes, and we want athletes that can move in multiple planes of motion, accelerate and decelerate, have plyometric ballistic power, be able to respond to stimuli such as reaction time, then we got to train in this manner. Now, that's not to say that there's not enough space to train our athletes in all three of these type of modalities. But the reason I'm showing you this is just because I want you to understand that we could really challenge synchronization, muscle recruitment, and rate code firing if we want to. We have the knowledge and the ability to do so in the gym. So that is all I have for you guys right now. I will be in touch very soon. Have a wonderful rest of your day.